Hi, welcome to this tutorial on the Poisson approximation to the binomial distribution. Now, in an earlier tutorial I showed you that if you had the random variable x, which was distributed as a binomial distribution with parameters n and p, and providing that n was more than or equal to 50 and p was less than or equal to 0.1, then x followed a Poisson distribution approximately with mean np. And remember, np is the mean of a binomial distribution. Now, this particular approximation is useful in certain conditions, these conditions, and it helps to simplify a calculation on the binomial distribution. And what I want to do is show you a typical example that you can expect to get that uses this approximation. So here's the example. I'll just read it out to you. A factory produces a particular electrical component, and on average 1 in 50 is faulty. And in a batch of 300 components taken at random, what is the probability of having at least 8 faulty components? Well, this particular model here is a binomial distribution. If we assume that the probabilities remain constant and independent at 1 in 50 being faulty, we've got a finite number of trials n being 300, and if we look at the probability of a success, that is a faulty item, being 1/50th, then as I say, we've got a binomial distribution. So we need to define a random variable x here, and I've done it here. Let x be the random variable number of faulty items, where x is distributed as a binomial distribution, n is 300, and the probability of getting a faulty item is 1/50th. Now, to work out the exact probability of getting at least 8 faulty components, we would need to work out the probability that x is greater than or equal to 8. Now, greater than or equal to 8 would mean we need to work out probability of getting 8 plus the probability of getting 9 and so on all the way up to 300, which is obviously very impractical. So we'd look at the converse and do 1 minus the probability that x is less than or equal to 7. Now, to work this out, what we would need to do is a very lengthy calculation, unless you are lucky enough to have a calculator, for instance, that could do the binomial probabilities for x less than or equal to 7. It's unlikely that you would have a set of tables where n was 300 and it gave you the cumulative probability for x being less than or equal to 7. So if you were doing this by hand, and I've done it for you just here, just to save a bit of time, you would have to do something along these kind of lines. 1 minus the probability x equals 0 plus 1 and so on all the way up to 7. And then work out for each probability the particular binomial probability using the formula that you see here. Okay? And that's quite lengthy to do on a calculator anyway. Working it out, you get 1 minus 0.745382 and so on, and then you end up with 0.25461 and so on. So what I'll do is I'll just put that answer 0.25461 and so on. That's the real answer. We'll just put it down in this corner here so that we don't forget it. Alright. What I'll do is I'll just remove this calculation and then we'll look at the problem again. Now, because we have n as 300 and it's greater than or equal to 50, and the probability of success is 1 in 50, and 1 in 50, 1/50th, as a decimal is 0.02, that is less than 0.1, then we can see that x must satisfy these conditions that we've now got a Poisson approximation. So let's just write that in here by saying that since n is more than 50, remember it's 300, p is less than 0.1, it was 0.02 for 1 in 50, then we can say that x follows a Poisson distribution, and we now need to work out the mean being n times p, 300 in this case times 1/50th. And if you do that on a calculator, you get 6. Try not to leave x as following a Poisson distribution with mean 6. Just don't write just that. Okay, x follows a binomial distribution, remember, up here. That's what the accurate distribution is. To say that is wrong. X doesn't follow a Poisson, but if we write the word approximately afterwards, then we've got a correct statement. Okay? So, going back to this, the probability x is more than or equal to 8 equals 1 minus the probability x is less than or equal to 7. We can do this with ease because it's very likely that 6, the mean of 6, is in a set of tables for the cumulative Poisson distribution. Okay, if we bring up a set of tables, here we are, typical set of tables which you'll find generally at the back of any statistics textbook or in a book of statistical tables. In this particular extract, we've got lambda equaling 6, that's the mean, equaling 6. We've got the observed values x going down here, and all we need to do is look for 7, and we have the probability of x being less than or equal to 7 given here, 0.7440. So all we need to do is just write that in as 1 minus 0.7440. It's a good idea when you're using tables just to say from tables, so I put that in brackets there. And if we do that subtraction, then what you get is 0.2560, and it's best to round this up. So if we round that up to say 3 decimal places, 0.256 to 3 decimal places. So this is the approximate value, 0.256, and remember the real value, the actual value, was 0.25461 and so on. So you can see that this is not bad as an approximation. And look at the amount of work that we had to do. Nothing really compared to if we had to work out the individual binomial probabilities. So you can see that this really is useful. But do remember, you can't apply it all the time. You've got to make sure that n is more than 50 and p is less than or equal to 0.1. Alright? Okay, well that brings us to the end of this tutorial, and I hope you've been able to follow that.